Okay, hi, we are back for our next astronomy lab video. Okay, so this one is going to be an interesting one. Supernova and nova explosions. Okay, here we go. So this one right here. Stellar explosions, novae and supernovae. A nova is singular and novae or novae, you say. In English, we say novae, so that would be plural. Supernova is singular, supernovae is plural. So these are all terms for different kinds of star explosions. So introduction. So I gotta make sure when I do this, when I start with the first page. So welcome to Lab 13, Stellar Explosions, Novae and Supernovae. Many stars produce violent explosions, particularly near the end of their lives. The most violent of these can, for short periods, produce luminosities comparable to that of an entire galaxy. Among these violent events are novae, X-ray bursts, supernovae, and gamma ray bursts. So imagine that, like a burst where it gives mostly gamma rays, which is the highest energetic electromagnetic waves. One consequence of these explosions is the production of many of the elements that occur in the universe, particularly the heavier ones. This lab investigates two examples of such explosions, both of which involve the accretion of matter onto a white dwarf from a companion in a binary star system. So both of the ones that they're going to explore in this lab are related to explosions that relate with a white dwarf. First, we discuss nova events, including the basic nova mechanism, with an introduction to the element production that occurs in such events. Second, we discuss an even more violent event, type 1A supernova explosions, which corresponds roughly to a runaway thermonuclear bomb with a mass equal to that of the sun. Oh my gosh. We will also show how type 1A supernovae can be used to determine the distance to galaxies that are very far away from us. Okay. So now we go to white dwarf. So I got to make sure that on this one, always start with the first page. I think that's the first one. Yeah, okay. So at the end of their stellar lives, medium mass stars become white dwarfs, extremely dense stellar remnants approximately the size of the Earth. So white dwarf is basically what our sun will eventually end up as. Yeah, our sun is a medium mass star, and it will turn into a white dwarf, and it will be a very dense star, and it will be the size of the Earth approximately. All main sequence stars with masses approximately 1 to 10 times the mass of the sun will become red giants before they die. Red giants eventually consume all their nuclear fuel. After ejection of the envelope, the cores of these stars shrink to the very hot, very dense objects that we call white dwarfs. A white dwarf is roughly the same size as the Earth, but has a mass comparable to that of the sun. The shell ejected by nova Cygni. Cygni means it's a nova that happened in the constellation of Cygnus in the 1992. So you see the nova occurred right here, nova explosion, and you can see the gas here emanating away from the central white dwarf. This is a white dwarf right here at the center. and it's ejecting the accumulated accretion disk that has accumulated on the mass on that white dwarf. So white dwarf density exercise. So a white dwarf is roughly the same size of the Earth, but has a mass comparable to that of the sun. We can use this information to estimate the density of a white dwarf. First, calculate the volume of the Earth, given that the radius of the Earth is 6.38 times 10 to the 8. So they're just using the volume of a sphere. And so you're going to take 4/3 pi, and then this is the radius of the Earth, and you're going to cube it. So because the white dwarf radius is similar to the radius of the Earth, they're going to use the radius of the Earth to calculate the volume of a typical white dwarf star, and then you get the answer here. So put in the numbers, put in the calculator, put in show the work for this. Then you put in the numbers here and see what you got. Then you go to question 2, and then you take but now the white dwarf's mass will not equal to the Earth's mass. It will equal to the sun's mass. So then you're going to take the mass of the sun, and you're going to divide by the volume that we just got. So the mass of the sun divided by the volume, and you're going to get the density of the white dwarf. And you're going to see that the density of the white dwarf is huge. The density of water is 1 gram per cubic centimeter, but the density of a white dwarf is very, very huge. So density of white dwarf star, in terms of kilogram per cubic meter, it's 1 times 10 to the 9th kilogram per cubic meter. But in terms of gram per cubic centimeter, in gram per cubic centimeter, because that's the units that they're having us calculate. So density of a white dwarf is the density of a white dwarf is about 106 grams per cubic centimeter. That seems a little bit too little. Hold on. Density of a white dwarf. The star standardized results. Educational Fair Use website. White dwarfs are used. Yeah, so they're about 1 million grams per cubic centimeter. Yeah, that's right. That's the answer. 1 million. We're expecting an answer in the vicinity of 10 to the 6th gram per cubic centimeter. That means the white dwarf is 1 million times denser than water. Imagine that. The density of water is 1 gram per cubic centimeter. The white dwarf star should roughly be of the order of 1 million gram per cubic centimeter, 1 million times denser than water. So that's the kind of density that we're expecting. So in calculating the density of a white dwarf star, sources have ranged from 10 to the 4th all the way to 10 to the 9th. So there's a wide range of possible answers, but the average of that is about 10 to the 6th power. Okay, so that's the kind of answer we are expecting. So give your answers to those, show your work. Okay, now let's go to the next one. Degeneracy. Because the material of a white dwarf acts like a degenerate gas, it does not expand as the temperature increases. If the material begins a thermonuclear reaction, there will be nothing to slow it down, leading to a thermonuclear runaway. So the extremely dense material in the white dwarf behaves like a degenerate gas. Although all gases are governed by the principles of quantum mechanics, degenerate gases behave rather differently than normal matter. As unusual property of a degenerate gas is that its pressure is independent of its temperature. So that means it doesn't obey the ideal gas law, the PV equals nRT. In a regular ideal gas, the bigger the temperature, the bigger the pressure will be. But in this one, the pressure is independent of its temperature, you see? So thus, contrary to our usual experience, if we were to heat a balloon filled with degenerate gas, it would not expand. This characteristic has significant consequences for thermonuclear reactions occurring under conditions of extreme high density. So if a thermonuclear reaction is ignited in matter, it quickly raises the temperature to very large values. For a normal ideal gas, this temperature increase raises the pressure, causing the hot gas to expand rapidly, you see? So this is kind of what happens in a typical gas, they're saying, okay? So if a thermonuclear reaction is ignited, it raises the temperature, and for a normal gas, the temperature increase raises the pressure, and therefore the pressure causes the gas to expand, you see? This process lowers the temperature and density, thereby slowing the thermonuclear reactions. And therefore the expanding gas is now gonna cool. And therefore the pressure is gonna lower, you see? Now with degenerate matter, look what happens. The situation is completely different. Since the pressure does not increase with the temperature, as the temperature increases, the thermonuclear fuel is heated, but not separated by the explosion. This result causes the reactions to go even faster because thermonuclear reaction rates increase rapidly with temperature. This process is called thermonuclear runaway and can lead to gigantic explosions. So that means you've got this compact gas in degenerate matter, and then all of a sudden, you're heating it, the pressure is not even rising, and then you basically have like a pressure cooker. Think of it that way. You have the volume is staying constant, and the gas is no longer expanding. So it's just gonna have a runaway effect, and it's just gonna explode. So thermonuclear ignition under degenerate conditions is thought to be a key component in nova explosions, X-ray bursts, type 1 supernova, and the helium flash in red giant stars, which is, we've studied that in the astronomy lecture class, if you remember. Stars like our sun will have an event called the helium flash when they die. Stars like our sun, however, will not undergo type 1 supernova or type 2 supernova, but they will have an event known as the helium flash, and then they will turn into a white dwarf. So the Chandrasekhar limit. White dwarfs have natural maximum mass of about 1.4 times the mass of the sun. So that's the heaviest that a white dwarf star can be. Theoretical astrophysicist Subramanian Chandrasekhar predicted that there was a limiting mass for white dwarf stars. No white dwarf could be stable against gravitational collapse if it exceeded this mass. So essentially what this is telling you is this chart is the mass of the star. If it's one solar mass, the radius of the solar units. So this vertical unit is giving you in terms of the radius of the sun, in terms of solar units. So a one solar mass white dwarf is going to be around what? Around maybe around 0.01. That's going to be almost 0.00. I would say 0.007, 0.007 of the radius of the sun, which means about the radius of the Earth, you see. So one solar mass white dwarf. But now as the mass of the white dwarf is increasing, what's happening? I'm adding more and more material in a smaller space. The gravity of the material is causing the white dwarf to start wanting to collapse, you see? So the heaviest I can make the white dwarf is 1.4 solar masses, you see? This is right around 1.4. And then at that point, the radius of the white dwarf is essentially like almost zero. It collapses, you see? So the lighter the white dwarf, the bigger the radius. You see, at 0.02 solar masses. You see. So contrary to intuition, as mass is added to the white dwarf, it shrinks. The limiting mass is defined as the point at which the radius would shrink to zero. No white dwarf can exist at that mass or beyond. And then, therefore, it must collapse to become a neutron star or a black hole. You see? So if I add more mass to the white dwarf might collapse even more. And then will turn into a neutron star or a black hole. But of course, white dwarfs never will turn into a true real life. White dwarfs will not turn into neutron stars. They will just die away eventually, and they will turn into what's known as a black dwarf. It's like black charcoal, essentially, dead black charcoal. But this is just saying, if I were to add mass to a white dwarf beyond the Chandrasekhar limit, then it would turn. I could potentially make it turn into a neutron star, or eventually a black hole if I add too much mass. So instruction: there's a plot of radius. Okay, good. Let's see, what do I do? I don't think there's much that you do here. Oh, okay. So then here I can just click, and it will tell me, depending on where I'm clicking, it will tell me the mass of that. Okay. It will tell me. So for example, if I want to know one solar mass, right there, one solar mass, why is it, you know what, let me minimize it. So one solar mass right there. Okay, one solar mass, 1.008. So roughly around the 1 point solar mass white dwarf, how big will it be? 0.0081 solar units. So what does that mean? 0.0081 solar units. So that means the radius of that white dwarf will be 0.0081 times the radius of the sun. They're given in solar units. So then we have to find the radius of the sun. You can Google that. Radius of sun. Okay, it's in miles, but I want it in meters is better. Okay, so this is the radius of the sun. 6.957 times 10 to the 8. 6.957 times 10 to the 5th, if you want it in kilometers. Okay, so let's just write it in meters for now. It doesn't matter, either kilometers or meters. So let's just say in, okay, you know what? Let's just do it in kilometers. 6.957 times 10 to the 5th kilometers. So 0.0081 times 6.957 times 10 to the 8 times 10 to the 5th kilometers. So that would be the radius of a white dwarf. That's about the mass of the sun, right? So then let's multiply that, 0.0081 times 6.957 times 10 to the 5th. Oh, that comes out to be 5,635 0.17 kilometers. That sounds like it's close to the radius of the Earth. Let me see. So then what is the radius of the Earth? So let's now say radius of Earth. Radius of Earth in kilometers. There you go. That's the radius of the Earth in kilometers, 6371. So radius of Earth is 6371 kilometers. You see. So yeah, so we're talking about a 1 solar mass white dwarf is slightly smaller than the radius of the Earth. So imagine the meaning of that, just to appreciate that even. So you have, imagine here is the, I'm going to erase this now. Imagine this is the real sun. This is the real sun here. Try to visualize this. So imagine this is the sun, right? And then the Earth size is something looks like this next to it. Next to the sun, the Earth probably looks like this. You see. Okay, then next to it, I'm going to draw a white dwarf. That's slightly smaller than the Earth. Yeah. Okay, so imagine the mass of this is 1 solar mass. This is 1 solar mass, 1 mass of sun. This is the Earth. So the mass, that's 1 mass of Earth. And then this one is 1 mass of sun. Imagine how much dense that is. Something that has the mass of this guy, you see, something that has the mass of that guy, and but its size is smaller than this guy. Now, how is that even possible? And what kind of star will end up like this with a 1 solar mass core? Remember, so how do white dwarfs, how are they formed? They are formed when stars that are between 1 to 10 solar masses die. So our sun will end up as a white dwarf. But when our sun dies, its core will not be as heavy as itself, you see. So when our sun dies, its core will be smaller than this. So it will be more like, maybe like this. I'm just visualizing it here. So when our sun dies, it will end up as a white dwarf like that, because our sun's mass is already 1 solar mass, you see. So when our sun dies and its core is left, only its core is left, how massive will its core be? Well, I'm just going to guess a number here. Its mass of the core might be something like 0.3 solar masses, let's say, or 0.2 solar masses. So in order to get a white dwarf that has 1 solar mass, a star that's maybe 7 or 8 solar masses needs to die. Do you see what I'm trying to say? Like at the upper end of that echelon, you know, so heavier star. When that guy is dead, it will produce a white dwarf that's 1 solar mass. You see? Now, how about the top, the one that's 10 solar mass? When that guy dies, When the 10 solar mass star dies, then you will produce the heaviest possible white dwarf, and that's 1.4 solar masses. And that one will be slightly bigger than this guy. Oh, actually, no, hold on. What are we saying? The opposite is true. See, I made a mistake now. The lighter the lighter the mass of the white dwarf, the bigger it actually is. This is counterintuitive. So our sun will most likely end up, let's just use this chart, for example. So go back to this chart. So let's say our sun ends up as a white dwarf that has 20% of the mass of the sun. So then we go to this chart, we say, where's 20%? Oh, you see, let's say our sun ends up as this kind of white dwarf right here. So then its radius is going to be, oops. Okay, right around there, 0.2 solar mass, 20% of the mass of the sun. So its radius is going to be 0.018 when our sun dies, 0.018. So when our sun dies, its radius will be 0.018 of the radius of the sun. So what will that be? What was the radius of the sun? 0.018, 6.9, I still remember it, 6.957 times 10 to the 5th kilometers, right? It's kind of weird that our sun will end up as a lighter white dwarf, but it's actually bigger, you see? The more mass you're adding on the white dwarf, the smaller it's getting. And it's starting to get denser and denser. So you're talking 0.018 times 6.957 times 10 to the 5th. Oh, 12,522.6 kilometers. Oh, that's about twice the size of the Earth. The Earth diameter is 6,000. Oh, okay. So then that means our sun will end up as a white dwarf that looks like this. Twice the size of the Earth. Twice the size of this guy. So it'll be something like this. Yeah. If I'm saying if it ends up with 20% of the mass of the sun, it'll be about 2 times bigger than our Earth. And of course, its density will not be as high as a 1 solar mass white dwarf. You see? Hope this is all making sense. A lot of math there. So this is 0.2 solar mass. But the heavier guy, like the one that's 10 solar mass white dwarf, when it dies, it might end up with a white dwarf that's maybe not 1.4, but close to 1.4, 1.3 or something solar mass white dwarf. Then it's going to be actually even smaller than this guy. It'll be like a little dot. It'll be like the size of the moon, maybe. Very small. Yeah, probably. Let's say it'll be the size of the moon by then. 1.3 solar mass. Okay, so now there's probably some exercise based on that. Okay, so use the Chandrasekhar limiting mass graph above to determine the following. What is the radius in solar units R of a white dwarf with a mass? Oh, okay, I just did that. So basically go over here, find the crosshair, take a picture of this, but try to get the solar mass to be exactly 1, you know? So you have to sort of play with it. And then take a picture of that. and then whatever solar units radius, then you put it here, and then you click submit based on that picture. And then in the next question, which of the following is most true statement when considering white dwarf density? Then you'll just answer it. I think that's it. There's no calculation on that one. That's good. So just one picture and one question. Two questions, I mean. Okay, so then you go to the novae. Okay, stellar explosions. In a binary star system consisting of a normal star and a white dwarf, the normal star may end up filling its Roche lobe and sending its material spiraling into the white dwarf. Nova explosions take place on the surface of white dwarfs in binary star systems that are composed of a white dwarf and a more normal star. So then when you have a star here, this is the white dwarf right here. This is a dead star. And if there was a companion binary star that's, let's say, a red and starting to die, so it's turning into a red giant, you see? So one of the stars needs to be already dead, which is, this is the nova, this is the white dwarf. And then this guy is starting to die, so it's going through its death process. So then it's turning into a red giant. So then what happens? The white dwarf is much smaller than the normal star. And then this is the Roche lobe and inner Lagrangian point. This is the inner Lagrangian point. So when this star starts to engulf, starts getting bigger and bigger and bigger, and it starts to fill its Roche lobe, then it starts to feed the mass. The gravity of the white dwarf starts sucking material from its companion star. Okay, through that Roche lobe. It's like a balloon that's releasing air. Imagine filling up a balloon so much that the pressure inside the air causes the air to leak out. So then this is going to start feeding this guy. So it says there's a unique gravitational potential energy contour in a binary system that intersects itself at one point, which is called the inner Lagrangian point. So that's this point right here. The interior of this contour defines two regions, one around each star, which is called Roche lobes. The Roche lobe corresponds to the area around the star in which the star's own gravity dominates. Oh, okay. So see, the white dwarf's gravity dominates in this blue region. The red giant's gravity dominates in the red region. And in this case, I believe we're assuming that the red giant is heavier. So that's why the center of mass is closer to the white dwarf in this picture, because this guy is the heavier one. So it says the normal star, however, may swell to, so it says the white dwarf is small and does not fill its Roche lobe. The normal star, however, may swell to fill its Roche lobe as it evolves. When this filling happens, matter from the surface of the star can be pulled through the Lagrangian point into the Roche lobe of the white dwarf. This material circles the white dwarf, forming a disk of matter that slowly spirals down to the surface of the white dwarf. This disk of matter is called an accretion disk. Okay? So this matter goes from here, starts getting pulled, because the gravity of the white dwarf is much stronger than the gravity of the red giant. So because it's so small and it's compact, so its gravity is strong, it can pull matter from its red companion giant. Okay, so let's see here, filling the Roche lobe. This animation illustrates a binary filling its Roche lobe and forming an accretion disk around the companion. See, it's starting to die. The star is starting to die. And you see the accretion disk starts to fill around. And this, of course, takes millions of years for this to happen. You see, so matter for the star's overflowing its Roche lobe, and then the matter is accreting around this white dwarf. I think that's it for that page, just showing that animation. So material that falls onto a white dwarf from a companion eventually heats to the point of thermonuclear fusion. So that's kind of what it was saying at the beginning. It turns into like this degenerate gas and starts to heat in a thermonuclear fusion. This process quickly leads to thermonuclear runaway until finally the layer explodes off the surface. You see? So that gas that is degenerate and under high temperatures, it's not expanding. As it's accreting around the white dwarf, it's going to reach such high temperatures that it's just going to explode. And that event is known as a nova and can repeat as long as the companion star feeds material into the white dwarf. See, and it can repeat as long as the companion star feeds material into the white dwarf. Why is that picture half not visible? Oh, okay, so in a nova explosion, a thin layer of mostly hydrogen, the rapid expanding and very hot shell that is ejected is responsible for the sudden rise in light output from the system. So maybe we could see, this is so interesting that it's worth seeing maybe like a YouTube video on it, so we can see a good animation. YouTube. Animation of a nova outburst. This guy, nova, supernova, short film. Okay, I don't want to see a supernova outburst yet. I want to see a nova outburst. Let's see here. No. Sirotis animation. Maybe this is the one. Let's look here. Well, this was the outburst that was created, but it wasn't that. I want to see something. Animation of a massive nova explosion from star system V906. This looks better. I'll give the audio for it. Yeah, you know, we want to hear the audio with it, of course. So now, the white dwarf itself is not the thing that's going to explode in a nova explosion. Only that accreted gas, that is a degenerate form of gas that's just exploding. Now, after the explosion ends, we should still see the white dwarf in the center, still remaining after millions of years. And then the companion will keep feeding it. That was a pretty good one. I wonder if there's one where they added some audio, novae and supernovae type 1. Nova outburst captured, best ever visible observations yet. Let's see this one.
Now and then, an obscure star briefly flares up, brightening up to 1 million times. It's an event called a nova. The star V906 Carinae erupted as a nova in 2018. Observations from 3 satellites provide new insights into what happened. NASA's Fermi mission has seen 14 novae since 2010. Before then, astronomers didn't think novae could glow in gamma rays, the highest energy light. When a white dwarf pulls material from a companion star, the gas forms a thickening layer that eventually erupts in a thermonuclear fireball. A nova is born,
Wow.
led by a team from Michigan State University. astronomers studied V906 Carinae using high-energy data from Fermi, NASA's New Star X-ray telescope, and invisible light from a Canadian satellite named Bright Toronto. Shaped by the orbital motion of the stars, the explosion debris first forms a thick, expanding ring around the system. Then, after 10 days or so, fast outflows, likely driven by residual fusion on the white dwarf, strike the ring. The resulting shockwaves produce gamma ray and optical flares that radiate away most of the nova's energy. These observations provide the first direct evidence that shockwaves can power most of a stellar explosion's visible light. Figuring out how they work in nearby novae will help us understand more powerful events much deeper in the cosmos.
Wow. Remember, as I was saying, there's so many good videos, animation, and stuff that you can watch that you could also put in with your discussions to help each other to understand this material about any of the topics that we are covering. You know, you could always search good materials. That was a really good one. I like that video because they also explained it a little bit and they showed some good animation. So you can kind of see that one, right? Very interesting, very, very. It's the wonder of the universe. Nucleosynthesis. Now you might say, besides being interesting in the fact that, okay, these explosions happen, what are they more interesting? What's the use of this knowing and even knowing that? Well, it ends up that a lot of the material in the periodic table that we know of are only produced during some of these exotic explosions. So if we go to the periodic table of matter that we know, periodic table, images. So let's say, just take any old periodic table. So it turns out that the materials up to like iron from, well, hydrogen and helium, these two materials, hydrogen and helium, were formed in the Big Bang. But then otherwise, the rest of the materials were all made in stars, up to iron. But the materials beyond iron were formed in these explosive events, explosions, silver, cadmium, and gold, and mercury, and all of these things. So they're formed in these exotic explosions. So we could even Google here periodic table materials made in star, maybe find some kind of chart. I know that there is a chart on this, and then they tell you where each of the materials is made. Which of these materials? Yes, I love this one. I've seen this one before. So, so notice this here, blue. I want to kind of expand on this. There you go. Okay, so you see the ones that are colored blue, hydrogen and helium, the Big Bang explosion created hydrogen and helium. And tiny bits of lithium. You see how there's a little sliver of lithium? So the Big Bang explosion created hydrogen, helium, and little bits of lithium. Then we get to dying low mass stars. So those would be, let's see, exploding massive stars. So dying low mass stars would be, our sun would be included in that list. So they would be stars like our sun or even lighter, up to 10 times solar mass. They're calling all of those low mass stars. In other words, all those stars that end up as white dwarfs. You see, all those stars that essentially end up as white dwarfs, including our sun, up to 10 times the mass of the sun, they created these elements of the periodic table: lithium, Carbon, well, of course, that's where we come from, carbon-based life. So we're byproduct of stars before our generation that made this material by thermonuclear fusion. Nitrogen, which is our atmosphere, right? Our atmosphere is 71% nitrogen. So it comes from dying low mass stars that lived and died before our solar system was ever even born. You see, little bits of helium, you see the yellow one, and also all these guys, zirconium, I think, morbidium, and so on, silver. See, Ag is silver. Sn, I think, is tin. Pb is lead. Ti, what is it? Ti, is that titanium? And then gold, a little bit of gold, platinum, and mercury. So those are all made in dying low mass stars. Okay. Then the other ones, exploding massive stars. So those would be anything that is beyond 10 solar masses, and which when they die as a supernova explosion. Type 2 supernova, they're called. Type 2 supernovas. So they produce those elements. They produce some of the carbon in our universe, some of the nitrogen, all of the oxygen we owe to them. So next time you breathe a little bit of air, look up at the heavy mass stars in the sky and say, thank you, God. In a sense, those are our gods. When we breathe air, thank you to the stars. Right? And then so then you get here exploding these massive stars, F, neon, sodium, mercury, aluminum, silicon, without which we wouldn't have computer technology, right? Because it's all silicon-based technology. Those all come from exploding stars, sulfur, chlorine, argon, and all of these other materials. All the ones that are green, essentially. Then comes exploding white dwarfs. Now, in the case of nova explosions, nova explosion is not actually an exploding white dwarf, because only the accretion disk around the white dwarf is exploding. So we would have to kind of look up to see what exactly elements a nova explosion creates. But I believe when they say exploding white dwarf, they're talking about the type 1a supernova, which we're about to talk about in this lab. That's when the white dwarf itself explodes. What does that one create? Well, that one creates a little bit of the silicon, sulfur, all these, most of the iron in our bodies, nickel, copper, zinc, all of these guys. Okay, so they're created by the exploding white dwarfs. Now, how about this orange one? We owe a lot of things to the orange one. Wow, merging neutron stars, orange. So all of these, look at that. RH, Ru, silver. All of these things we owe to two neutron stars that are merging. You see? And then there are this one, TC. I'm not sure why that color is different. The atomic number 43 is a bit different. Oh, then there's two elements that are made by cosmic ray fission. That's something different. Fission of an atom by cosmic rays. So that's boron and beryllium and a little bit of the lithium. So it's kind of nice to see the breakdown of how these things are made and how we owe our lives to the production of these materials. Okay, so let's now go back. So nucleosynthesis refers to the formation of elements by nuclear reactions. Most elements that are heavier than helium are produced by nuclear reactions in the cores of stars. Well, that's what I was saying earlier. Less massive main sequence stars can produce isotopes of elements up to around carbon, which has proton number of 6. Was that right? You see, so in other words, less dying low mass stars, you see how they can produce lithium and carbon, but also up to nitrogen. They do produce nitrogen also. You see? And then the other guys, we owe to massive stars for that. We owe our lives to both the low mass stars and the massive stars. And the most massive main sequence stars can produce isotopes up to iron, which has a proton number of 26. You see? So iron is up to 26. They're also producing, exploding massive stars. They are producing a little bit of the CO, cobalt, nickel, and copper, zinc, and even these guys. They're producing up to krypton and rubidium. You see, and that's after that it kind of slows down. You see, then you get here the production of heavier elements as well as many isotopes of elements that are lighter than iron, which are not produced in normal stars, require processes that take place in stars only after they leave the main sequence. While some of these elements and isotopes can be produced by reactions taking place during the red giant phase, many can only be produced in violent stellar explosions at or near the end of a star's life. One such source of nucleosynthesis is nova outbursts. In the most violent nova explosions, for a few seconds, the temperatures can exceed 250 million degrees. So remember how earlier I was saying, well, we need to look at what nova explosion in particular produces. Well, that's what they're going to show here in this graph. What kind of things a nova explosion can produce. Under such conditions, nuclear reactions, which are ordinarily very slow, can become very fast, and new isotopes, which would not be produced otherwise, may be rapidly synthesized. So you see, so this is showing you as a star is dying, and well, as the nova outburst is happening, what products it is producing. So this simulation examines the abundance of elemental isotopes as the nova explosion evolves. Click the forward button to move forward one frame or back button. The play button lets you view the animation as a movie, either once or as a continuous loop. The pause button lets you to pause the animation. Use the animation rate slider to set the animation rate. The chart in the simulator is arranged according to the proton number, vertical axis, and the neutron number, horizontal axis. Thus, each square is an isotope of an element. You see that? So remember that as you go up, the element is changing, and as you go to the right, in other words, isotopes are elements that have the same proton number, but they differ by their neutron number. So all those elements in the horizontal are isotopes of that different element. So the color of a square in the chart indicates the relative number of atoms of that isotope produced by that type after the explosion. The color bar at the top right of the main window provides a key to the colors shown in each square of the chart. Cycles are closed paths of element production. Some cycles that are important in nova explosions can be displayed by clicking the checkboxes. Okay, so let's see what happens. Let me just see if I zoom in a bit. See, that's what I don't like about the zooming is you lose this side. Okay, so then let's see here. If I go, no, so then let's go animation rate. So go forward. No, let's start from the beginning. Pause. No. Loop. Oh, okay, hold on. Go back, go back, go back. Okay, now 1 second in this animation is probably like thousands of years in real life, you see. So this is as the nova is happening. You see, shows cycles. So the temperature, hot nova conditions, temperature 2.5 times 10 to the 8 Kelvin. So that would be like saying, if I change that to million, that would be like saying 1, 2, that'd be like saying 250 million Kelvin. That's the temperature of a nova. And the density of the gas of a nova is 500 grams per cubic centimeter, which is 500 times denser than the water. Okay, so now let's see what elements are being made. So now let's go a step at a time. Wait, is it going forward? Maybe go higher animation rate. Why is it that slow? Something is not working. I've done this too before, but abundance. What happened here? Let's see here. Okay, stop. Okay. To go step, 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 step. I guess I need to press play first and then go loop. Why isn't it going? Maybe go the faster way. Go. Why isn't it working? Click the button to move forward 1 frame at a time. It just stopped working, not even showing anything. No loop. Loop. You know what? Let me just refresh the page. Oops, it went all the way to the beginning. No. Okay, I think now it's gonna work. Seems like it's good. Okay, so animation page. So now go. I want to start from the beginning. Okay, so I want to see here. See, it's looping to almost 1,000 seconds, then it's coming back to the beginning. Okay, now can I go a step at a time? Oh, there you go. Okay, there you go. Okay, so let's just say 1 second in the animation is 1,000 years of real life. I'm not sure how it works, but so at 0 seconds, nothing has been produced in that nova explosion. So then at 1 second, then at 2 seconds, oh, damn it, it stopped working again. I don't know why it's getting stuck. refresh. Maybe if I just press, okay. I'm not even gonna press play, I think. Just go like that. So 2 seconds, what has been made? Okay, so you see the oxygen, this element of oxygen has been made, this isotope. So oxygen has 8 protons. The typical oxygen has 8 protons, but then there are different isotopes of oxygen. You see the green, the blue, red, and this other green. F is fluorine. And so this isotope has already been made. Now, abundance, look at the abundance. So the red one is the most abundant. That means in fluorine, this isotope, the first isotope of fluorine, it has been made in abundance in that explosion. And then neon, the second isotope has been made in abundance, but the fourth isotopes of neon is the most abundant. It's orange, you see. So that means all these elements are being made as this thing is exploding, this gas surrounding the white dwarf, and different isotopes are being made at different times and at different abundances. So like silicon, Si, you see the yellow, 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 and then green. The blue is the least abundance. So those isotopes haven't been made yet. Now let's go forward. Let's go forward. Let's go forward. You see, all these other elements are now being made. All these other isotopes are being made at different abundances. Keep going forward. Keep going forward. Now, as time goes on, I believe the heavier elements are going to be made. Argon, different isotopes of argon. Oh, now we're already at 1,000. Oh, it went by really quick after that. Now, if I want to go a slower rate, I go animation rate slower. Oh no, I think even if you go animation rate slow, oh, it looks like it wants to always go to 2, 4, almost 8 seconds, then almost 16 seconds. So even if you reduce the animation rate, oh, then it's also going to be, what's the CNO? Oh, these other elements are being made. Carbon, nitrogen, oxygen, neon, and sodium, these elements. Magnesium, aluminum, silicon. So then the next one is 126 seconds. And then finally, by the 1,000-second mark, which is like millions of years later, you know. Okay, so now here, start. For this exercise, use the nucleosynthesis simulator above. For brevity, we will abbreviate the proton number by Z and the neutron number by N. One cycle that should be familiar from discussion of energy production in main sequence stars is the CNO cycle. Click on CNO at the bottom and notice the CNO cycle. White line is seen to follow the path ZN. Oh, okay, so then let's just click this one. So the white line goes what here? Let's see here. Oh, so it follows here. It's almost like a zigzag. Let's see here. One cycle that should be familiar with this from discussion of energy production is the CNO cycle. So we learned in the astronomy lecture portion that the CNO cycle is a way of making energy that uses carbon, nitrogen, and oxygen as a catalyst. So click on CNO at the bottom and notice that CNO cycle white line is seen to follow the path ZN 66 to 76. So where's that 66 to 76? So 66, would be 6, and this is 6. You see, this is 6 right here, 6 neutrons. So this is 6 protons, 6 neutrons. So then from there, it goes where? Then it goes to 7, 6, which means it goes up. So then the next thing that it produces is nitrogen with the same number of neutrons, 6 neutrons, but 7 protons. So it goes vertically up, you see. Then it goes what? 6, 7. Then the next thing it produces, it goes down and produces a heavier isotope of carbon. 6 proteins, 7 neutrons. 6 protons and 7 neutrons. Then it's going to go all the way up to this. Let's see here. Then it goes to 8, 7. God, this is so intriguing. Then it goes all the way up to 8, 7. So it's going to produce an oxygen with 8 protons and 7 neutrons. Then it's going to go down and produce a nitrogen with 7 protons, but 8 neutrons, right? Then 7, 8. Then it goes back to 6, 6. Then it goes back to 6, 6, and this whole cycle repeats. It's like boom, 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 down, 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 like that. Wow. So then the other ones have another cycle, Hot Cno Cycle. Oh, intriguing, very intriguing. So it says carbon, nitrogen, oxygen, fluorine. Use the chart plus the table of Z values and symbols to fill in the gaps in the Cno cycle table. Carbon, nitrogen to 12, nitrogen 13 to what? To oxygen 15 to what? To carbon 12. Drag and drop the selection from the following list. So for that one, basically take a picture of this one, maybe a little bit enlarged picture to show this. So you would go a little bit enlarged of this one, and then that would back your answer to how you're doing this. Then put this in the order and then submit the answer. And then is there another question there? Oh, I thought there was another one. I think that's it for that one. So basically that'll be your basis for your answer here. That picture that you take of this. Then you go to question 2. A cycle of great importance in nova explosion is called the Hot Cno Cycle, which extends the Cno cycle. Click the Hot Cno button at the bottom of the simulator and note which isotopes are involved in this cycle. Okay, so then you just uncheck this one and you check this one. Okay, so then there is slight difference, it looks like, from the other one for that one. So then you take a picture of that one and then you answer this one based off of that. Then you go to the next one. Drag and drop the isotopes below into the correct order from the least abundant to the most abundant isotopes produced 1 second after the nova explosion. Oh, okay. Then you go to the animation and you go back to where it was 1 second. You see? And then so maybe you uncheck this and all you do is just go back to when this one was 1 second. And then I would zoom in on this part like this, take a picture of the whole thing with all of these unchecked, and then focus on the color code of the abundances, right? And then answer those questions based on abundance. Drag and drop your selection from the list to complete the answer. So the least abundant would be the more bluer one, right? Would be the more bluer one, and the most abundant will be the more orange or red one. And then you would base your answer based on that. So with one picture with that, and then base your answer off of that. And then the next one, drag and drop the isotopes below into the correct order from the least abundant to the most abundant. So then you take another picture for that one, and then you do this one, same thing. So base it off of that. That's pretty cool. So you're learning kind of how all of the chemistry that we learn, how those elements come into being, and how our whole lives really matter on all these elements being made. Okay, is that it for this? I think that's it for this section. Okay, then you go to the next one. I think that's the last one. Oh, now we're gonna go to when the actual white dwarf itself explodes. That's called type 1a supernovae. Oh man, this is a gigantic explosion now. So a bigger explosion. A type 1a supernovae is similar to a regular novae, except the material from the other star accumulates too quickly. The mass of the white dwarf climbs and climbs and eventually passes the Chandrasekhar limit. At that point, nuclear runaway occurs, and eventually the white dwarf is destroyed in a massive explosion. And that's the one that we saw in the periodic table that produces the exploding white dwarf. All these light blue stuff, most of the iron in your body, nickel, copper, all of this, all those are exploding white dwarfs have produced that in previous generations before our system ever came into being. Okay, so then in type 1a supernova, matter accretes onto white dwarf through an accretion ring. As matter accumulates on the white dwarf, its mass increases. Eventually, it becomes unstable because it exceeds the Chandrasekhar limit. And essentially, the entire star is consumed within a fraction of a second with a gigantic thermonuclear explosion. A type 1a supernova may be likened to the explosion of a thermonuclear bomb approximately the size of the Earth, but containing the mass of the sun. So remember how we said earlier that white dwarfs are the size of the Earth, their typical size, but they are the mass of the sun. So imagine taking that and just immediately exploding that. Thermonuclear explosion consumes the white dwarf. The fuel of the fusion bomb is carbon and oxygen. Since the white dwarfs that explode as type 1a supernova are composed primarily of these elements. So white dwarfs are primarily made of carbon and oxygen, and that's what is doing the explosion. The runaway fusion reaction is thought to start in carbon and produces typically about 0.6 to 0.8 solar masses of radioactive nickel. So this is all the chemistry behind what's exploding. So the fusion reaction is starting in carbon and producing typically about 0.6 to 0.8 solar masses, of radioactive nickel. Since the white dwarf at the time of the explosion is the Chandrasekhar mass, the upper limiting mass for the white dwarf of about 1.4 solar masses, this implies that about half of the mass of the original white dwarf is fused in the type 1a explosion. So you see, like if the mass of the white dwarf was 1.4 solar masses, about half of it, 0.6 to 0.8 of it, is being included in this explosion that's about to happen. Not all of it per se, but about half. But that's enough to create such a huge explosion that it's going to blow that whole white dwarf into smithereens. It's just blow it all into piece. A standard candle. Now you say, what does a candle have to do with this? Well, let's read on. Because the white dwarfs that explode as type 1a supernovae are all the same mass and composition, more or less, right? They're more tend to be about the same mass as the Earth and the same composition. They all explode with the same energy and peak absolute magnitude. For this reason, they are called the standard candles. We can use these fixed absolute magnitude and their measured apparent magnitude to find the distance modulus. Oh, now we go back to the distance modulus. So since we know that all type 1a supernovae should be about the same brightness, so their absolute magnitude should be about the same, then depending on how far away the star is from us, they're going to be dimmer and dimmer. So their apparent magnitude is going to be less. and then that's going to change their distance modulus. And thus, it's going to change the distance to the supernova. Type 1a supernova, such supernova 1994D in NGC 4526, see image, are also important because of the striking regularity of their light curves. A light curve is a graph of a star's apparent magnitude versus time. The light curves for different type 1a supernovae usually peak at the same absolute blue or visual magnitude of about negative 19.5. So that means we expect the supernovae, their absolute magnitude to be negative 19.5. Looking through a blue filter, a blue or visual. Remember, that's the one we called blue BD color index, right? So we learned so many things now. Everything is starting to come together, you know. So absolute visual or blue or visual magnitude about negative 19.5 with an uncertainty of only about 0.2 to 0.3 magnitudes. So that means they're going to be within 19.5 by only a difference of 0.2 or 0.3. Therefore, it says we can use a type 1a supernova as a distance indicator by comparing its apparent magnitude at peak with the standard absolute magnitude and using this inverse square intensity law. An object such as this, which has a known absolute magnitude and thus can be used to determine distances, is called the standard candle. So light curve for supernova 1994 D. So this actually is an actual supernova that happened in the year 1994. So the diagram shows light curves of supernova 1994. Select the blue box to view the blue light curve. Select the visible box to view the visible light curve. So if I'm looking through blue filter, that means I'm filtering out most of the light but the blue. And so its brightness looks like this. The apparent magnitude, so the apparent magnitude is going from, let's see, these are the number of days, you see, the measured from the zero. Zero means when it reaches the brightest that it could possibly be. Right, let's see here. No, oh, sorry. This is the apparent magnitude. So in other words, it starts out with an apparent magnitude of 10 days prior to the actual brightest possible. The apparent magnitude is like a 14.5. That means you can't see it with your naked eye, right? But as the days go by, as you're approaching zero, what's the apparent magnitude? It's 12, which means you still can't see it with your naked eye, but it's a lot brighter than being 14 or 14.5. See, so as the apparent brightness is increasing all the way to 12, that means it's looking brighter and brighter to telescopes, but it's still not visible to the naked eye, of course. Then it's decaying. So after 10 days, it has already decayed. But by the 80th day, after the maximum peak, by the 80th day, it's no longer that spectacular anymore in the sky. You see, so by the 80th day, the apparent magnitude has decreased to what, like about almost 16. Remember how the apparent magnitude works? The less the number, the brighter the something appears. So 12 is still pretty bright appearing as compared to 14 or 16. You see? So now in the visible light curve, oh, okay, visible means yellow filter, right? Through the yellow filter. So in the yellow filter, its brightness stays brighter for longer, you see? So it goes, but it stays brighter longer. And even up to the 80th day, it still appears in the visible spectrum, it still appears 15 apparent magnitude. But that's still not possible to see with the naked eye. So you still need a telescope to see it. But interestingly, at peak, they're both about apparent magnitude at 12 with a blue filter or the visible filter. You see? So this is the visible, this is the blue. So the blue filter, the brightness decays quicker. Okay, so now what do we do here? The distance modulus. So the distance modulus calculator allows you to calculate either the apparent magnitude little m, the absolute magnitude big M, or the distance. Choose the unknown value from the drop-down menu. Choose the units of the distance from the drop-down menu. Enter the known values and press the calculate button to calculate the unknown value. Press the clear button to clear the value. And there's probably some exercise based on that, right? You would cut the fun out of the lab if there's no exercise based on that. So now we go to exercise. Okay, in 1994, the Type 1a supernova 1994D was observed in NGC 45, and the light curves were recorded using both blue and visible light filters. A filter limits the color or wavelength of light that is under the examination. See the light curves for supernova 1994D above to see these light curves given in units of apparent magnitude for a number of days before and after the supernova. What is the peak apparent magnitude of supernova 1994D? Well, that's pretty obvious. Not much math for that. So you just take a picture of this, and both in the blue and the visible, the apparent magnitude is 12. You see, the peak apparent magnitude at day number 0. And by day number 0, they're measuring it from the brightest peak. So this is -10. In other words, even before the actual supernova has exploded, 10 days before, you can kind of already tell something is about to happen. So that star is about to explode 10 days before it. It's starting to get bright, right? In other words, it's down here, it's starting to get bright. So somebody observed it already. A bunch of astronomers noticed it and go, oh, okay, something is happening here. And you can see in this picture, you see here, spiral galaxy, and then the supernova is right there. It's off to the side of the galaxy. Now, if you notice in this picture, it's very, very interesting. The center of that galaxy is what's known as a supermassive black hole. And look how bright that center of the galaxy is. But you look off to the side, and there's a white dwarf star that's exploding. It's almost as bright as the center of that galaxy. Right? So it's like amazing. Off to the side. That's how the astronomers can spot it. A star is dying there. A white dwarf star is about to explode. And 10 days before, they can already tell. You see? Oh my gosh. So, of course, the answer there is pretty easy. This one, you just need a picture of this one. Just a picture of this right here. And then your answer. Right? And then go to question 2. Now calculate the distance in parsecs to the galaxy using the distance modulus calculator above. Hint, as this is type 1a supernova, we can use the standard candle peak absolute magnitude of -19.5. So that means we know that -19.5. So then with this one, you're going to do 2 things. You're going to put the apparent magnitude that you got here. Let's say you got an apparent magnitude of 10. Absolute magnitude, you're going to put -19.5. And then the distance to that, they want to calculate the distance to that star in what? In parsecs? Yeah, in parsecs. So now we just say the distance in parsecs. What is this? Oh, no, yeah. We're calculating the distance. And then we say calculate. Oh my gosh. So that means that star or that galaxy is 7.943 million parsecs away. You see, 10 to the 6th is a million. So 7.943, 10 to the 6th parsecs away. So then you would take a picture of this, right, and put it here. 7.936 times 10 to the 6th parsecs, right? And then you would actually show the work for that, for how you get that. Remember what the equation was from the previous lab? 10 to the power, what was it? Something like 10 to the power m minus m plus the 5 over the 5. And that was the distance. That gave you the distance to the galaxy or the star in units of parsecs already, right? So then you put the little m and the big M, and that should give you the same answer as what you just used, the table that you used. So for that one, you're showing a picture of this, a picture of what answer when you submit it, whether it's correct or not, and the picture, well, basically you're showing your work, the distance equation. And let's see what we can expect. What is the distance to that supernova? What was the name of the supernova? Supernova 1994D. Supernova 1994D. So what is the distance to that supernova? Supernova 1994D. By D, they mean it's probably the 4th supernova observed in that year. So they probably, yeah, I believe they name it in order of the, if it's 1994A, then the first one supernova observed that year. B is the second one observed, C, D, so on. By the way, how many supernovas are observed every year? How many supernovas are observed per year? It's kind of like how many hurricanes there are in a year, but in hurricanes, we name them according to, like, we give them letters of the alphabet, right? Like A, B, C, but we give it the person's name, like Hurricane Amber, let's say, you know. Then the next hurricane of the season, we say Hurricane Boris, you know, a guy's name, or so then we go from letters of the alphabet. So supernovas, we name them by the year we discovered and by the ABC. So how many supernovas observed per year? Rubin Observatory is predicted to discover 3 to 4 million supernova during its 10-year survey. That's a lot. Hold on. List of supernovae. Distance of light years. Oh, these are all the supernovae that we've discovered. So this just gives you everything, the whole list. Oh, wow. There aren't that many. Supernovae. Oh, this is in the year 1885, 185. So, of course, they didn't have a picture of it back then, you know, in the year 185. So, wow, that is beautiful. But now we've actually pictured it. And then you can actually see, okay, what is its apparent magnitude in the sky by now? What kind of supernova is it? If it's a 1A, then it would be the type of supernova that we just saw, the white dwarf exploding. If it's a type 2, then it's a heavy mass star that's exploding. And we haven't even talked about that, a heavy mass star that's exploding. That's a type 2 supernova. Let's see. Oh, then it tells you which galaxy this is in. Milky Way galaxy. Milky Way galaxy. And it gives you a little description of that. So this is 3886 in the year 386 AD. God, these are wonderful pictures, imagine. So essentially, this is what's giving us kind of a lot of the heavier elements. Wow. Beautiful pictures, amazing. So it's giving you the apparent magnitude, 1.5. 1.5 is actually, that's pretty high. You should be able to see that with your naked eye. Yeah, you should be able to see that with a naked eye. And even -4, I don't know why there's a question mark there. Man, if it's truly -4, that would be so bright appearing in the sky. Oh, the other thing I'm not sure, is that apparent magnitude when it first occurred, or is it the apparent magnitude now? Ah, you see, that could be the apparent magnitude that it had when it first occurred. That's kind of high for the apparent magnitude to be 1.5 now. You see, it's by now it should probably be dimmer, but then we would have to look that up, you know, depending on what is. So is that the apparent magnitude originally and when the supernova happened, or now? So I'm not sure about that one. So these are the other ones. Supernova 393, 1006 is very famous. 1054. And then 1181. So now if we go to modern times, 1994, well, it seems like that's the most famous one in the year 1994 is the D. There could have been other ones that year, but that was a type 1A, you see. So what was this third column? Oh, the distance in light years. So the distance of that star was what? It's 50 million light years. You see? So just from that, can you predict what the answers to this question should be to the 1994 D type 1A supernova? Oh, it was discovered. Actually, I know Alex Filipenko. He's a famous astronomer back up in UC Berkeley. He was discovered by his team, Alex Filipenko's team, in 1994 D. So if it's 50 million light years, how do you convert from light years to parsecs? So 50 million light years. Then I can say 3.26 light years is 1 parsec. So we can get an approximate value of what the distance to that galaxy should be. $50 divided by 3.26. Okay, about 15.3 times 10 to the 6th light years. I mean, sorry, parsecs. Parsec. I forgot what was is it PC, right? Is the symbol? Is it PC or PS? I think it's PC. So 15.3 times 10 to the 6, 15.3 million parsecs. So that's kind of what we expect that answer to be just from that table. And this gives you a little bit more information on it if you just want to just read up on it. 1994, it gives you a little bit more detail, who discovered it, history of the supernova observation. Then it tells you peak magnitude, peak apparent magnitude, gives you the host galaxy, or the redshifts, the distance in light years, and then where is it in the sky, declination angle, and the right ascension, and which constellation is it in? It's in the constellation of Virgo, if you want to find it in the sky. That's where that supernova would be. Intriguing stuff, huh? Intriguing. Just amazing. I think that's it for that. So that's called a standard candle. So we're using the apparent brightness of a supernova and the fact that we know its absolute luminosity should be roughly 19.5. Then from there, we're using it as a way to calculate distances to galaxies. You see? And I think that's it. Okay, guys, have a good one. So this is going to be our next lab. The following one after that is going to be about neutron stars and pulsars. We're getting into really astrophysics, really. This is called astrophysics. Neutron stars and pulsars, general relativity, black holes, evidence for dark matter. Good stuff. Okay.